So, in this lecture, we study the t-shift. In the book, it's called Translation on the t-variable. This is section 10.5. For the moment, we're skipping 10.4. So here is the entire theory. If f big is the transform of the small f, then multiplying this image f by the exponential here, the original changed in a special way. So the t-variable is shifted here in f, and also we are multiplying by the step function u t minus a. Recall that the step function is defined to be 0 when t is between 0 and a, 1 when t is bigger than a. So it has such a jump. If here is a, in front of a it's 0, then it becomes 1. The Laplace transform of the step function is given here. This is one of the important formulas in our table. Now, I will do some example to show you how this works. Examples. From the book, section 10.5. Here is number 2. Given is the big F. One image, it has the form e minus s minus e negative 3s. 2s, 3s doesn't matter. And divide by s squared. We want to find the original, the small f. So we see these exponentials here and we think about t-shift. I shall break this into functions. Write this way: exponential minus s 1 over s squared minus exponential negative 2s 1 over s squared. Well, let's correct this to 3 because it's 3 in the book. Okay, 3s. Now, on purpose, I wrote the exponentials first, and then in these places we see one recognizable image. This is the Laplace transform of t. So I can write this exponential minus s Laplace t minus exponential negative 3s Laplace t. And here we are ready to use the t-shift formula. Multiplying image by s reflects in shifting the variable t and multiplying the original by the step function. So this will be Laplace transform u t minus 1. In the first case, a is 1. T minus 1, shifting t. This is the first term, minus Laplace u t minus 3 times t minus 3, shifting t by 3. So that's how we invert the two terms, and now we collect everything in one place inside one single L. U t minus 1 t minus 1 minus u t minus 3 t minus 3. Inside the braces we find our original. So let's write the answer f of t u t minus 1 times t minus 1 and minus u t minus 3 t minus 3. This function is our original. Moving further, here is number 4. We are given big F of s. This time it's e negative s minus e 2 minus 2s, like that. Divide by s minus 1. Again, I shall break this in two terms, putting exponentials in front. 1 over s minus 1, first term, minus exponential 2 minus 2s, 1 over s minus 1. What to do with this exponential here? This exponential, I can write exponential squared times exponential negative 2s. So e squared is just a coefficient. I'll just keep it in front. And 1 over s minus 1, this is the Laplace transform et. That's what I'm going to use here. So I'm writing now the big F will become e minus s Laplace et minus e squared e minus 2s Laplace et. E squared is just a coefficient, it will stay here. And for these two terms, I'm going to use the t shift, multiplying image by exponential. So this will be Laplace u t minus 1, first case a is 1, exponential t minus 1, minus e squared, keep it in front, Laplace u t minus 2, exponential t minus 2. Okay, so this is it. Electing everything inside L, we can find the original, and it's visible very well. The original will be, from the first term we have u t minus 1 exponential t minus 1 minus, keep this coefficient, e squared u t minus 2 exponential t minus 2. And that's it. This is our answer. Moving further, number 6. Okay. In number 6, we are given f big to be s times exponential minus s on top, divided by s squared plus pi squared. So I shall rewrite it with the exponential in front, like that. And at this point I can recognize, and everybody with some practice will recognize, that this term here, it's already image. This equals Laplace transform cosine pi t, one of our basic formulas. So now the big F can be written exponential minus s Laplace cosine pi t. And using the t shift, this becomes Laplace u t minus 1, because a is 1, cosine pi t minus 1. Everywhere when we see t, we write t minus 1. That's how it works. So what is our original then? This will be ft inside L, u t minus 1, cosine. I shall multiply inside here, it will be pi t minus pi. This can be simplified. I can use a simple formula for cosine difference to angles. Cosine x minus y, cosine x cosine y, plus sine x sine y. With this formula, cosine pi t minus pi will become cosine pi t cosine pi plus sine pi t sine pi, and sine pi is 0. Cosine pi is negative 1. And then I can write my answer ft this way: negative u t minus 1 cosine pi t. This is our original. Very good. Moving further, let's jump to number 10. Here we have this big F. This is written 2s e negative pi s minus e negative 2 pi s. This is all on the top, and all this divided by s squared plus 4. So again, I will break this in two terms, adding exponentials in front, and this coefficient 2 also in front, like that. 2 exponential minus pi s, s over s squared plus 4, minus 2 exponential negative 2 pi s, s over s squared plus 4. S squared plus 4 is also very familiar, easily recognizable. This will equal Laplace cosine 2t. One of the basic formulas, where k is now 2. Okay, continuing this work, I'm writing 2 times exponential negative pi s Laplace cosine 2t minus 2 times exponential negative 2 pi s Laplace cosine 2t. And for these two terms, now I'm going to use the t shift. We keep these two in front all the time. Equals Laplace. In this case, a is pi, so I'm writing u t minus pi cosine 2 in the place of t, 2 minus pi. Of course, that's the first term. Minus 2 Laplace u t minus 2 pi, and here cosine 2 t minus 2 pi. Okay, I'm bringing everything inside. I can find the original. Here is the original ft, 2 times u t minus pi cosine, and I can multiply by 2 inside the cosine, and becomes 2t minus 2 pi minus 2 u t minus 2 pi cosine 2t minus 4 pi. And then I remember that 2 pi is a period, 4 pi is a period. This here is just cosine 2t, and this will be cosine 2t. I can write ft equals 2 times u t minus pi cosine 2t minus 2 times u t minus 2 pi, again cosine 2t. Common factor. 2 times cosine 2t is a common factor. Why not factor this out? And I shall put brackets here. There will be u t minus pi minus u t minus 2 pi. That's the answer simplified. So this was number 10. Now I think we are ready to see how to solve differential equations, and I shall do one simple differential equation. Solve the equation x second plus 9x equals ft, where the function will be defined this way. It's 0 when t is between 0 and 2 pi, and it is, let's say, 6 when t is greater or equal to 2 pi. And we shall take also 0 initial conditions, x 0 to be 0, x prime 0 to be 0. So let's solve this function, this equation. Applying Laplace to both sides, we have Laplace x second plus 9 times Laplace x equals Laplace f. Now we are using formulas for derivatives, and we also have to find Laplace of f. Here are the formulas: minus x prime 0, minus sx 0, plus s squared big X of s, plus 9 times big X of s, the Laplace transform of the small x. That's right again, big X of s, this is the Laplace transform of x of t. On the right side we have Laplace of f. So what is this? I shall just write Laplace f one more time. Here, at this moment, we remember that we have 0 initial conditions. All this will be 0. Factoring the big X, I can write big X times x squared plus 9 equals Laplace of f. Laplace f. Looking at the definition, we can use the definition for Laplace transform and write this integral 0 infinity ft exponential minus st dt. The function is 0 between 0 and 2 pi, and from 2 pi to infinity it's 6. So this integral becomes 6 times from 2 pi to infinity exponential minus st dt. That's easy to integrate. Here we have 6 exponential minus st divided by negative s between 2 pi and infinity. At infinity we take limit, and this limit will be 0. We have seen this many times. So minus value of 2 pi with 2 negatives becomes plus. This will be 6 exponential negative 2 pi s over s. That's the Laplace transform of f. It looks sort of familiar, and indeed you can see that the function f actually can be written this way: 6 times u step function t minus 2 pi. And then using the Laplace transform of the step function, you get the same answer. If you cannot express f in terms of u, better go with the definition and compute some simple integral. Now, solving for the big X, we have 6 exponential negative 2 pi s over s squared plus 9. This we can write with exponential in front like that. And I shall write 6 in front also. Let's organize some space for this 6. Coefficient 6 would stay here. And here we have 1 over s squared plus 9. Now this rational function we had to break in partial fractions. The theory requires to write 1 over s squared plus 9 in the form unknown coefficient over s plus bs plus c unknown coefficients s squared plus 9. Then writing common denominator, and with some computation you can assign s to be 0 then, and comparing coefficients for s squared for s, you can find a, b, and c. Now I want to use the short formula which I gave you before. The formula, I shall write it here again. The formula goes like that: 1 over s squared plus a is 1 over a parenthesis 1 over s minus s a squared plus a. Any a which is non-zero. So according to this formula, I can write immediately my decomposition. 1 over 9, 1 over s minus s over a squared plus 9. Okay, now we can invert this very easily. What is in the parentheses is recognizable. First we have Laplace of 1, then we have Laplace of cosine 3t. This is 1/9 Laplace of 1 minus Laplace cosine 3t. And then returning to the big, well, why not we write just like that, 1/9 Laplace 1 minus cosine 3t, these two together. Returning to the big X now is 6 times over 9 exponential negative 2 pi s Laplace 1 minus cosine 3t. Look at this. We're ready to use the t-shift. For a will be 2 pi. Excuse me. So first we reduce by 3 here, so we have 2/3 Laplace u t minus 2 pi. Now take the function 1 minus cosine 3t. Everywhere in the place of t you put t minus 2 pi. So this will be 1 minus cosine 3 t minus 2 pi, like that. And we can see our solution. X small t will be 2/3, this coefficient carries over, and from inside we read u t minus 2 pi 1 minus cosine, let's multiply 3t minus 6 pi. And 6 pi is a period, so all this is just cosine 3t. Here finally xt is 2/3 u t minus 2 pi 1 minus cosine 3t. This is our solution. Okay, we're ready for another equation. And let's solve also this. Solve the equation x second plus 9x equals, I shall just change the function f a little bit and make it this way. Let this be 3 when t is between 0 and pi, and 0 when t is greater or equal to pi. Again with 0 initial conditions to focus on the essential part, the t-shift. Now, how to find the Laplace transform of the function f? Laplace of f, function is 3 between 0 and pi, and then 0, so I can just go between 0 and pi, integrating 3 exponential minus st dt. And this integral is quite simple. 3 times exponential minus st, or negative s, 0 pi. So this will be 3 exponential minus pi s minus 1 over negative s. Something like this we inverted in the previous examples. Now, I want to show that this function can be written in terms of the step function also. Look at this. Take 1 minus u t minus a. How does it look like? This will be 1 when t is between 0 and a, and 0 after that. Because between 0 and a u is 0 and on the left side we have just 1, then on the right side of a, u becomes 1 and the difference is 0. So keeping this in mind and looking at the function f, we can write f of t like 3 times 1 minus u t minus pi. And then we can find the Laplace image by using this representation. Laplace f will be 3 times Laplace 1 minus Laplace u t minus pi. This will be 3 times 1 over s minus e negative pi s over s. That's the same thing we have here. And it's even written in a more convenient form. Either way, either using the definition or writing in terms of u. If you cannot write your function in terms of u, go with the definition. Now, applying Laplace to the equation, apply Laplace transform to the equation. On the left side, we get the same thing like before, because the left side is the same, initial conditions are the same. So this will bring to big X s squared plus 9 equals Laplace f, which is 3 times 1 over s minus exponential minus pi s. I shall write it this way, 1 over s. Solving for the big X, this will be 3 times 1 over s squared plus 9 minus 3 times exponential minus pi s, and same thing here. We already know how to invert this expression. So this will be 3 times 1/9, 1 over s minus decomposition from the formula, minus 3 over 9 exponential negative pi s, 1 over s minus s squared plus 9. Okay, we know the origin of this thing in the parentheses. I'm replacing it. In the meantime, divide by 3, reduce by 3. So we have 1/3 of plus 1 minus cosine 3t minus 1/3 exponential minus pi s or plus 1 minus cosine 3t. For the second term, we need the t shift. First term, we rewrite 1 minus cosine 3t. And here, 1/3 we keep. This becomes Laplace u t minus pi 1 minus cosine 3 times t minus pi here. In place of t minus pi. Okay. And then collecting everything inside L, and we can see our solution. Xt will be 1/3 1 minus cosine 3t minus 1/3 u t minus pi 1 minus cosine 3t minus 3 pi. Okay, that's what happens. What is 3t minus 3 pi? Again, using cosine difference of two angles, this is cosine 3t, cosine 3 pi, and then plus sine 3t, sine 3 pi, which is 0, so just this. Cosine 3 pi is actually -1. And we have xt equals 1/3 1 minus cosine 3t minus 1/3 u t minus pi 1 plus cosine 3t. This solution. it can be simplified a little bit, removing parentheses, regrouping. So let me show you. This will be 1/3 minus 1/3 cosine 3t minus 1/3 u t minus pi and minus 1/3 cosine 3t. Times u t minus pi. Here we can write this 1/3 1 minus u t minus pi and minus 1/3 1 plus u t minus pi and all this cosine 3t. That's how you can write the solution. Well, maybe this is enough for today. We continue later at another lecture.